This video is looking at the force on a current carrying conductor in a magnetic field. So we have a magnet producing a magnetic field. This might be North Pole, South Pole, and we have a current carrying conductor passing through current I. So we've got our North and South Pole there. That means we've got a magnetic field from north to south, and the direction of the magnetic field, B, is the direction that a little North Pole would like to travel in. And we've got this wire, there's a length L of the wire within the magnetic field. And we're going to use our right-hand slat rule to work out the direction of force on this current carrying conductor. So here's our right-hand slat rule. We've got one finger here for current, several fingers here for magnetic field, and slap, that's the direction of the force. So let's have a look at this. We've got a current moving to the right, we've got the magnetic field going up, so the force on this conductor must be towards you, out of the page. So we've got our force coming out of the page, and the size of that force we calculate using our equation F equals BIL, where F is the force measured in Newton, B is the magnetic field strength, in Tesla, I is the current, of course, in amp, and L is the length of wire inside the magnetic field, and of course it's measured in meters. So here's an equation we've got. Here's the problem. A 20 centimeter length of wire is carrying a 0.6 amp current perpendicular to the magnetic field and experiences a force of 0.50 Newton. Calculate the strength of the magnetic field. So we've got a wire of length L. The length is 20 centimeters. The current is equal to 0.60 amp, and the force that the wire experiences is 0.50 Newton. Calculate the magnetic field strength. Let's come over here. Here's our equation. F equals BIL. We're given the force, the current, and the length, and we're to calculate the magnetic field strength. So let's rearrange this equation. Rearrange, divide both sides by I upon L, and we get magnetic field strength equals F divided by I over L is equal to 0.5 divided by the current, 0.6 divided by the length, and note the length, 20 centimeters, is 0.2 meters. So the magnetic field strength is going to be 4.2, and the units Tesla. Okay, here's a second question. We've got a swing here. We've got that big horseshoe magnet again, and we've got these wires hanging down as we demonstrated in class the other day, and we're told that when the current flows through this loop, the swing moves in the direction A. The swing is moving this direction, so that's the direction of the force. Use the right hand slap rule to determine the direction the current is flowing through the wire. So let's have a look at this. Our right hand slap rule, we've got the force going to the right. Which direction is the magnetic field? This is the north pole and this is the south pole, so our magnetic field is from north to south. So we've got force, magnetic field going this way, so the current must be going into the page, from the front to the back, into the page. The second part of this question is the student then decides to reverse the direction the swing moves. So instead of it moving right to left, he now wants it to move left to right. He wants it to move this way. Describe two ways that the student could achieve this. So how could we get this swing to move the other way? We could reverse the current, so we could change the positive and negative of the power supply over, or we could turn the magnet upside down. So instead of it being north and south, we would turn it around to be south and north. Either of these ways will change the direction of the force on that current carrying conductor. Next, we're asked to calculate the size of the force on the swing given that the magnet width is 12 centimeters. So that's L is equal to 12 centimeters. The magnetic field strength is 2.5 Tesla and the current is equal to 3 amp. What then is the force that this swing will experience? And we use F equals BIL. The force on the current carrying conductor is equal to the magnetic field strength times the current times the length in newtons, in Tesla, in amp, and in meters. So the force is equal to magnetic field times current times length, and remember 12 centimeters is 12 by 10 to the negative 2 meter, or 0.12 meter times 0.12. So the force on that is equal to 0.9 force in Newton.